So this session is called the multiverse session. And before I get into the specifics of what I want to share with you, time and entropy in the multiverse, let me just say a few words about the multiverse to make sure we're all on the same page, including the many non-physicists whom we're so happy to have here. Multiverse, parallel universes are very controversial. That makes them a lot of fun. The physicists here have many colleagues who like them, like Alex Valenkin here, who feels that they're inevitable, and others like Paul Steinhardt, who will grumble and say, this is not science. And sometimes you even get an advisor disagreeing with his advisee about whether they exist, like David Gross versus Frank Wilczek here, Lisa Randall, the open-minded. People who work in cosmology on inflation, like Andre Linde, Alan Booth, and the Albrecht tend to be pretty open to it, Steinhardt being the one exception. And I think part of the reason there's been so much acrimony about this is because you never get as good a debate going as when people think they're talking about the same thing and are actually talking about two different things. A great way to generate more heat than light. And there are a number of different things which people tend to call parallel universes. So we don't mix them up here. First of all, what we mean by our universe in astronomy is not everything that exists. That's what we often call a multiverse or whatever. Rather, we tend to mean the finite region of space, the spherical region from which light has had time to get here so far during the 13.7 billion years since our Big Bang. We sometimes call this our Hubble volume or our observable universe as well. So if that's the universe, then if space simply goes on forever, like Euclid had us believe, and we've all thought as kids, then there are many of those. So I like to call that the level 1 multiverse. And then there is the stuff that we've heard about from a number of speakers here, including the Albrecht, where you have many of those. We call that the level 2 multiverse, where you have regions which are effectively separate Big Bangs that all came out of inflation, producing a giant, super messy space-time. And they're so far apart that you can't get there even from one to the other, even if you travel forever at the speed of light, because as you try to go from one to the other, there's constantly new space being created between them by inflation, faster than you can ever go through them. Then there's a third kind that we heard two very nice talks about mentioning this morning. David Wallace and Simon Saunders have worked a lot on the multiverses of quantum mechanics. We had a nice debate about it the other night, or yesterday at lunch, which are the ones that John just mentioned are in a sense right here. The motivation from them comes not from studying the really big stuff, which gave the first two levels, but the small stuff of the micro world. The basic idea being that we know that little particles can be in several places at the same time. So if I'm made of these little particles, then perhaps I can be in several places at the same time. And presumably the particles that make up our whole universe can be in two different states at the same time. One where the conference is organized here in Copenhagen, and one where it's organized on Tahiti. Then there's a fourth level multiverse, which is so crazy that it has perhaps only a single person who really believes in them. That's me. Which is that not only that even the fundamental laws of physics could be different. And where are these different kinds? Well, the first kind, if they exist, they're just really, really far away in space, in the same space. The second ones are also far away in space, except so far away now that there was a bunch of messy inflation going on between here and there, so we can never get there. The third kind, well, they are off in the so-called Hilbert space, this infinite dimensional mathematical space where quantum mechanics lives. And the fourth kind, if it exists, is often some sort of platonic space of all mathematical structures. What are they like? The first kind is very much like here, except if you go to a school in the parallel universe of that first kind, far, far away, you'll learn different things in history class, because the particles started out in different places over there, and the planets were in different places, and you just learn different things about the wars and so on that took place there. But you'll learn the same stuff in physics class. In the second kind, you might learn different things in physics class too, because the effective solutions to string theory or whatever the truth may be might have turned out different there. This thing here, ironically, even though as you can read in Peter Bernstein's book about Hugh Everett, this was very controversial at the time, nothing qualitatively new there. Whereas in the fourth level, you can get fundamentally different laws of physics, like Pac-Man or something like that. Good. That was a brief introduction, just so you can sort future speakers a little bit into different boxes in your brain and don't mix up different kinds of parallel universe ideas you get exposed to. Now, let me turn to the main topic of my own talk, which is this. So we have had a lot of exciting discussion about the arrow of time in our universe, how things seem to have been, how things seem to be getting more and more messy and more high entropy, and what we should make about this. So the motivation for this, first of all, involves to a great extent of it, this entropy problem, which Sean Carroll explained so nicely, and I would very much recommend in particular a very well articulated paper by Sean Carroll and his colleague H. Tam, which you can find on the archive, where they come back to this basic point that if our universe is very simple now, then, giving rise to this arrow of time, then it would have been even simpler in the past, and even simpler in the past, and even simpler in the past. So simply saying that if we start out in a very simple state, this with inflation or whatever, feels very contrived, because we're just replacing the explanation of saying it's a great fluke that is like this now by an even bigger fluke required earlier. Here's a quote I find very interesting by a well-known philosopher. Thinking that entropy has anything to do with what we know about a system is a bad, misleading mistake. Does someone recognize this?
I guess it's David Albert.
This is David Albert from yesterday's lunch, that's right. And David attributed this more or less to Gibbs, and presented it nicely as an antithesis to Boltzmann, and as an antithesis to Gibbs. I think whenever there's a controversy in science, it's very interesting to look at the whole spectrum of opinions you can have on it and look at the two extremes. So if this is one extreme, then what I'm going to do today is take the opposite extreme, the Gibbs viewpoint, and say, I think in fact, what we know about a system is something very important to take into account. My opinion is that if I'm interested in using physics, to make predictions about my future, then even knowing the entire quantum state of everything, the whole multiverse, is neither enough, nor is it in fact necessary. I need to really take into account what I know about where I am in this big reality, both where I am in three-dimensional space and where I am in the quantum mechanical Hilbert space, as I'll clarify in a sec. And it's not necessary for me either to know everything. I just need to know a lot about what's nearby in my space. It doesn't matter greatly if I want to predict how this is going to fall, what's happening in the Andromeda galaxy right now. Nor does it matter greatly what's happening elsewhere in Hilbert space, in some parallel universe which is completely decoherent from this one. So this is very relevant, because if we take seriously what we heard about inflation, that you start out our universe with some hot, dense state described by perhaps some wave function psi, and then maybe it's even smooth and homogeneous and isotropic, and then this evolves. Then these quantum fluctuations, which we all thank for the giving rise ultimately to the structure we see today, the galaxies and the stars, etc., they were generated by quantum processes, right? And if we started out with a symmetric state that was on average the same, that was homogeneous and isotropic, then on average this whole thing was going to be homogeneous now too, but the total state is going to be. But it's of course going to split into many, many decoherent branches. Klaus Kiefer, David Polarski, and others have written some very nice papers about how this works. So the states today, what's happened is we had this simple quantum state early on, which has evolved into a superposition of a bunch of very classical seeming universes like ours, but with the galaxies in different places. and also a superposition of a bunch of dead stuff, which just failed to inflate or failed to make galaxies, whatever. And if I want to make predictions for what's going to happen when I throw my laser pointer up in the air, and I happen to know that I'm in this galaxy and Andromeda is over there, I can ignore these other branches, and I should ignore them, just like I should take into account on my position in space. So we have to be very careful to avoid loose talk and say the quantum state is this, without specifying whether we're talking about the density matrix of everything, including all these branches, or just one particular branch. Likewise, we have to be very careful to not conflate talking about, when we say this the entropy, do we mean the entropy of the whole state with everything, or do we mean the entropy, for instance, of this particular branch? Because they can typically be very different. In fact, the entropy of the whole shebang might be 0. And you're not going to find hardly anyone in this room who's going to argue that the entropy of what we see that's relevant to us is 0. Right? Even if the total quantum state is a pure state. So Feynman put it very nicely and said that it's sometimes very convenient to take everything out there, and in geek speak for the physicists, I mean all degrees of freedom, and split them into two parts. The part that we care about, which we usually call the object or our system, and the rest, which we usually call the environment. And then in many cases, we can just focus on the dynamics of what happens within these degrees of freedom we care about. In fact, most of our quantum textbooks do that when they study the harmonic oscillator, the hydrogen atom, or whatever. But once in a while, the interaction between this and this environment matters. This is what gives rise, for example, to decoherence and fluctuations and entropy increase in a very well-known way. Now, I feel that to really get to the bottom of this and fully understand what's going on with entropy, we need to generalize this and also include the third part, which is us, the degrees of freedom that are aware of everything else. And then we get this picture sketched out like this, where you have this Hamiltonian, for those of you who are physicists, and then there's a part that just regulates how this evolves by itself, this by itself, this by itself, and there are different interactions between them, which have very, very different effects. This interaction, as I said, has to do with decoherence and entropy increase. This part, which I'm going to talk more about now, has to do with observation and so the other half of sort of puzzles and mysteries that plague us so much in quantum mechanics. Let me be a little specific and talk about each of these processes at a time. If I just look at an object, let's take a completely an experiment, completely isolated playing card here, for instance. Suppose it's not interacting with anything at all, and there's no air, no vibrations. If I balance it perfectly on its perfectly sharp tip, because it's a toy experiment, it will fall down by the Schrödinger equation into a superposition of left and right like this. So far, the card hasn't been interacting with anything else. So if it started out with 0 entropy, still it's 0 entropy. We knew the quantum state initially. We knew it afterwards, the superposition of this and this. We call it unitary evolution. I'm going to, throughout my talk, assume that the evolution of the whole shebang is unitary, so no wave function collapse, and to see where that leads. But then, as was pointed out by Dieter Zeh in 1970 and worked out in a large body of work by Wojtek Zurek and many others since, big things like playing cards, they don't act classically because they're big, but they act classically because they're so hard to isolate from the rest. So you tend to get a lot of interactions between them and the green stuff, this environment. Air molecules bounce off of them, etc., and find out kind of where they are. And a simple two-state system, for those of you who are not physicists, can be described in quantum mechanics by a 2x2 table of numbers we call a density matrix. And in this case, this 0.5 here means there's a 0.5 probability, loosely speaking, of it being like that, and 0.5 probability of it being like that. But then the numbers that are off the diagonal say that it isn't really there or there. It's kind of there and there at the same time. And if you just do the math of quantum mechanics and figure out what happens to this table of numbers when you take into account this interaction, these other numbers on the side go away and become zeros, and it becomes more like in practice that the thing is there or there, you just don't know it. Okay. Now, if you look at something instead, then you're getting an interaction between you and it, an entanglement. So in this case, I bet, this is me here, I bet $100 that it was going to come down face up. So here, when I look and I see it there, I become happy, here I become sad. The state of me becomes linked to the state of the card. So the total wave function initially is, here I am hopeful, 10 seconds later, the card is there and there at the same time, I don't know anything about it. But now, information has been transferred to me, and the whole state of the world is either I'm happy and it's up, or I'm sad and it's down. And what Everett realized in the 50s was that feels kind of like the whole universe is sort of split into two pieces. And this decoherence thing that's so well understood explains why these two branches of reality never can communicate with each other again. When I talk about observer here, it doesn't have to be a human observer at all. All the math is exactly the same regardless of whether it's a human or a mouse or Jan's robot or even a photon doing things. It just has to do with exchange of information. And when you work through examples like this and you calculate the entropy, which for the physicists in the audience, I'm taking to mean just the von Neumann entropy minus trace rho log rho, what you find is that the second law of thermodynamics just becomes a little bit generalized. So instead of saying just blanket statement that the entropy can never decrease, you find that it can never decrease the entropy of an object unless it interacts with the subject. So the entropy, in other words, can never decrease unless you have an interaction here. And conversely, entropy can never increase unless you have an interaction here. So if the object isn't interacting with anything, entropy stays constant. Interact with the environment, entropy increases. Interact with you, it decreases. And in the paper I posted last week, which you can download, there are some equations. What happens in practice? This one here is very well known for decoherence. Here's an analogous one I quite like for the most general observation you can do, showing what happens to the density matrix there. I'm not going to dwell on any of these details because I want to turn now to something I personally found very surprising when I applied this to inflation and cosmology, because it turns out that at first it seemed like even though I can reduce the entropy of something by looking carefully at it, that would be hopeless for explaining why things look so simple out there in Copenhagen. Because if I look at a typical system like some gas or whatever, I'm only going to reduce its entropy by 1 bit for every bit that I measure about it. In my brain, I don't know about your brain, but I have a very hard time remembering even like phone numbers these days. And if I can only remember a megabyte, I can only reduce the entropy of the universe, you think, by 10⁶ bits or bytes, when in fact we want to try to understand why it's gone down from 10 to the 120 or so, maybe down to 10 to the 20. So I worked out, but that's not true for all states. In particular, here's a simple toy model, which I wrote down, which I created just to make it a little bit like inflation. We have a very big space-time. Just for simplicity, let's take this space and split it into little voxels, okay? It can be a Planck size each, or cubic millimeter each, so it doesn't really matter. Okay. And let's say each voxel can either be spin up or spin down, or it can be either, it's called habitable if it's green, or uninhabitable if it's red. Okay? And in large parts of it, each voxel is just completely uncorrelated with every other. But then there are these big swaths of stuff where it's entirely habitable. Kind of like inflation can take big regions, contiguous regions, and do something to them. Okay? Suppose our observable universe is much smaller than a typical scale of these green regions. That means that when we look at our thing, either we're entirely within one of these habitable patches, or we're in a kind of messy patch like this. And you can write down exactly the quantum density matrix for this. Fine, okay. And then you can look what happens when you start making measurements. Never mind the fully detailed equations here. Let me just plot what the results are. And what you find is this. You find that if you happen to be in a messy region like this, the P-def-like region, then the entropy that you have for the rest of your universe just drops linearly. You measure 50 bits, you've reduced its entropy by 50 bits. I just want to say, I think it's very important to realize that I haven't assumed any physics here whatsoever. I'm just using the Schrödinger equation. I'm just saying that if you make it very simple, if you put yourself into the equation as well, this is the kind of thing which happens. And I would encourage everybody to be very careful when they talk about the entropy, to actually calculate the entropy of the universe, given what you already know about your position in it. Because then you get a very powerful mechanism for sometimes lowering it. Let me not say anything about whether we should be averaging the express energy tensor to get classical GR, except that this formalism shows you when this is and isn't a good approximation, and in fact, some recent incorrect claims by various people that dark energy can be explained away by superhorizon scale fluctuations can be explained as using this approximation in a case where it shouldn't be used. For a long time, we were told that there were two different kinds of death we could choose between. This is the way the world ends, not with a bang, but a whimper. Either the universe was going to expand forever, and it was going to end with a big chill. Everything was going to get diluted away, and it was going to get cold and miserable. Or everything was going to come crashing back on itself in a big crunch. And then Robert Caldwell and collaborators came and gave us the big rip, a third doomsday scenario, where the dark energy, instead of diluting as the universe expands, anti-dilutes. And in a finite time in the future, it's infinitely dense and just rips everything apart. And I just want to add to that the big snap. Another key thing which has come up in a number of talks here, and many people here, including Rafael Busso, have said very interesting things about, is how much information is there really in a region of space? How many degrees of freedom are there really? And you'll hear more from Rafael momentarily here. And there are basically three logically possible answers. If I ask, suppose I take a region of the universe, a sphere of diameter 100 million light years, say, and I just watch as space expands. Either the number of degrees of freedom here is going to increase, or it's going to stay constant. Sorry, either it's going to change, or it's going to stay constant, or it was infinite to start with, so I can't tell whether it increased or not. Those are the only three real possibilities. And if the number of degrees of freedom are increasing, that's extremely problematic, because then it goes against all the basic quantum mechanics. You have to have a new add-on law of physics which says what state they should be born into, etc. So there are issues. If it's infinite, that would make Raphael very unhappy. Much of the evidence from the holographic principle, etc., suggests that that's not the way it is. So the third option, that there's a finite number of degrees of freedom, is also kind of troubling. Because suppose there's only a finite number of degrees of freedom in this volume. You can interpret that as that there's, at some fundamental level, some sort of granularity of space in a very loose sense. I'm not talking voxels, but it would feel very weird if you just kept expanding this forever until there was less than 1 degree of freedom in your whole observable horizon. Surely life would feel kind of different if you were reduced to 1 bit or less. And as soon as this sort of granularity scale expanded up to be the size of a proton, we would expect nuclear physics to start being a little bit different. And some atoms that are now stable might be unstable, and vice versa. If after it's expanded more up to so that the granularity scale reaches atoms, atomic physics would start to act differently, and we would almost certainly die. And so that's the big snap. Just like if you have something you're approximating is continuous, like a rubber band, if you stretch it enough, the fact that it is in fact finite, made of a finite number of things, atoms in this case, is going to cause something bad to happen. This is very confusing though, because I'm not standing here either as just a doomsday prophet saying, we're all going to snap, because in the simplest models of some sort of granular space, just 30 seconds, what you find is that long before you get killed by this, because your atoms fall apart and stuff, long before that, you find that gamma ray bursts, in particular, high energy and low energy gamma rays travel at different speeds. And what looks like a flash like this gets spread out in time. And there are very sharp bounds already. So the simplest kind of models you can write down for some kind of granular space are already ruled out, actually, by observations. So to summarize this, I feel that there is something I like, there is a degree of freedom problem we have, where you have these three options for what happens when space just expands and expands and expands. And they're all problematic. So whatever the resolution of this is, we're going to learn something very fundamental. Thank you very much.